But we know the reaction. And also we can write it down. It's going to be really easy. Don't tell people this.
Did it go well this time?
Yes.
All right. Let us begin.
And no, it's not.
So you just like
All right, number 37. Number 37. Let's talk about that. Just one last go round on this whole trig domain range kind of thing with arc sine, arc cosine. Remember, arc sine has a restricted domain and a restricted output, actually. Sine has a restricted output but not a restricted domain. Does that make sense? What's the output of sine? Between -1 and 1, right? So sine, okay, so we, and this is how I mean, I always have to think about it this way too. It's not automatic for me. Sine, the output is -1 to 1. So arc sine, what would be -1 to 1? The input, right? Because we interchange the inputs and outputs. Okay? So sine outputs are -1 to 1, so arc sine, the inputs are -1 to 1. All right, now with sine, you can have any input, right? I mean, the sine graph goes from -infinity to infinity. But it repeats a bunch of those values, right? So pi thirds, sine is √3/2. 2 pi thirds, sine is √3/2, right? Well, if you interchange the inputs and outputs, now all of a sudden that means you'd have multiple outputs, and you can't do that in a function. You can only have one output, right? So we restricted sine's input. So if I was to draw the sine graph here, we said we need to restrict it from -pi² to pi², right, for its inputs. That means the outputs of arc sine have to be between -pi² and pi². So this answer here, right, if we restrict the sine inputs to -pi² to pi², which by the way is 1.57 negative to positive 1.57. So if we restrict the sine inputs from -1.57 to 1.57, then that means the outputs of arc sine have to be between -1.57 and 1.57. So is there any way this output could equal 5? No. Okay? So that would be one way to explain that this has to be between -pi² and pi². Now, did anybody try typing their calculator? And maybe we talked about this one. No, we did. I talked about this one. Did anybody try typing that in? If you try typing it in and hit Control Enter so you get a decimal, you get -1.28 something. Now, is that surprising? Why not? Okay. 3 pi² is roughly 4.71, right? So if you were going to do the sine of 5, so what Cody's saying is if you do sine of 5, you would come all the way around to here somewhere, right? So sine of 5. But the arc sine, you don't measure it this way. We have to measure it between -pi² and pi², which means we would measure it this way. Well, how much is left? All the way around 6.28, right? So if this is 5, there'd be 1.28 left there. Now we're going backwards, so it's -1.28. So it's the same value, okay? And again, like we did yesterday, I did one where we put 2 pi thirds in here, or it was something like that. If we do the sine of 2 pi thirds, that's over in this quadrant. That's √3/2. But if we do the arc sine of √3/2, what do we get? Pi thirds, right? We get the first quadrant one, not the second quadrant one, because it has to be, again, between -pi² and pi². Okay, so that's the reasoning for 37. So then remember we said, so what we learned from that is that arc sine of the sine of x, they are inverse functions. They should cancel each other out. You should get x, but only if x is between -pi² and pi². Only in that instance will these cancel each other out because we have a domain restriction. However, if we do it this way, There is no restriction. If we do it in this order, this will always be true. Think about this. What are the inputs for arcsine? We just said it a minute ago. Between -1 and 1, right? Inputs have to be between -1 and 1. We couldn't do sine of arcsine of 5, right? If I ask you what sine of arcsine of 5, I hope you would all write, no solution. There isn't. You can't do that. You can't do the arcsine of 5. The inputs have to be between -1 and 1, otherwise there is no answer, okay? So if I put in a number that's between -1 and 1, like √3/2, the arcsine of √3/2 is pi thirds. What's the sine of pi thirds? √3/2. So you will always get back x as long as you stay within the domain, but you have to stay within the domain because you can't put anything in that's between -1 and 1. See, this one's different. You can put things in here that are not between -pi halves and pi halves. See, I can put in 2 pi thirds here. Sine of 2 pi thirds is √3/2. Arcsine of √3/2 is pi thirds. I don't get the same thing out. So see the difference. Now, the similar example, and I did it yesterday, and I think, okay, that was that. I think it helps to make sense. If I do this, okay, what do we say that equals? That equals the absolute value of x. Because would it be legal to put a negative in for x? Would it be legal to put a negative in for x? Yes, because I can put a -4 in here for x, square it, that's 16. Square root of 16 is 4. You don't get the same thing you put in. We put in -4, we got out 4. Okay? We need the bars to turn it to positive, because a negative would be legal to put in. However, if we do this in the other order, what's the answer to that? Because could x be negative in this problem? X could not be negative in this problem because you can't do square root of negative. As long as we're doing real numbers, x could not be negative here. All right? So we do the square root, then square it. We know that x that comes out is positive because the x had to be positive to start with. And so we'll get the same thing out. So the order that you do these inverses to each other can matter. Now with natural log and e to the x, it doesn't matter. ln e to the x is x. E to the ln x is x. There are no domain issues. Okay, now this is kind of a technicality, and it's usually not an issue. It's usually not something we have to worry about. As we go through the year and we get better at the basic ideas of what's going on, then we will look at these technicalities more. Okay, and we will talk more about them. They'll become an issue you have to really deal with. On the gateway test this week, not going to be an issue. Not going to be something you really worry about. Okay? All right, let's look at number 39. So 39, they gave you the function, what was it, arcsine of sine x, and you were supposed to do that derivative. Okay, now, these are inverse functions. They should cancel each other out. So this should equal just plain old x, right? Right? This should, unless there's a domain issue, which it turns out there is, but these cancel each other out, so really this should be x. The derivative of x is 1, right? So we would expect the derivative of this to be 1, unless there's some domain issue to deal with. Well, it turns out there is. When we do it in this order, arcsine has to be restricted from -pi halves to pi halves, so it might not just equal x. Okay? So, let's go ahead and do our rule, though. Let's just do our derivative rule. Okay? The rule was the derivative of arcsine is 1 over the square root of 1 minus u, which would be sine squared. It's okay to write the sine squared like that in this instance. That's fine. Times the derivative of the inside. Oh, wait. I should make a comment right now, too, because several people asked me about this. When we talk about the chain rule, we said there's 3 parts. Derivative of the outside, leave the inside alone, do the derivative of the inside. Where in what I just did I leave the inside alone? When I put the sign right there, right? The rule was 1 over square root of 1 minus u squared. The u is the inside. So when I put sine right here and squared it, that was the leave the inside alone part. I worked with several people who put a sign here because they were thinking, oh, I got to leave the inside alone, so they put a sign there. Then they did the derivative of the inside. Okay? So on some of these, it's a little bit tricky. I've also seen that when people do a natural log problem. If I've got ln x squared plus 3, and I would do the derivative. Remember, the derivative rule for ln u is 1 over u times u prime. Where are you leaving the inside alone? Well, when you put the u on the bottom, that's when you're leaving the inside alone. The derivative of ln is 1 over the inside, and then times the derivative of the inside. So when I do this, I do 1 over x squared plus 3. When I write the x squared plus 3 there, that's the part where I'm leaving the inside alone. Okay? And then times the derivative of the inside, which is that. Okay, so I think that was throwing a few people off here. And then I also talked with one person who was wanting to do a product rule here. This is not ln times this. Okay, it's ln of this. It's a function, just like sine. Those are not, you know, if this would have been ln x times x squared plus 3, now you got a product rule. Okay, so those are two different things. All right, a couple little things that I've seen come up. All right, so back to this. Derivative of the inside is cosine. All right, now we have to go back to trig and remember this. What's 1 minus sine squared?
Cosine squared x.
Cosine squared x. Okay, now here's where this thing we just talked about a minute ago comes in. What's the square root of cosine squared? Absolute value. So this ends up being cosine of x all over the absolute value of cosine of x, because cosine could be negative. You square it, it's positive. You square root it, your final answer is positive, and the cosine was negative. So you can't do cosine squared, square root, and just get cosine. Technically, you've got to get absolute value of cosine. Okay, now, let's talk about what that is. This is basically 1. Cosine over cosine is going to be 1. However, the bottom will always be positive. The top could be negative. So really, this right here is plus or minus 1 is what that is. That's plus or minus 1. All right? If cosine's positive, both the top and bottom will be positive, you get 1. If cosine's negative, the bottom will be positive, the top will be negative, you'll get negative. Okay? So the answer to this is essentially plus or minus 1. Do you remember, did you see that graph there on that page? You know, that zigzag? I call that the Charlie Brown graph. Okay, right? The up and down thing. Look at the slope of that thing. What are the slopes? 1 and negative 1, right? 1 and negative 1. So, plus or minus 1. Okay? So that's where that all comes from. All right. So, with that said, now let's focus on our gateway test, the rest of today. So, 13, 15, 17, 19, any of those, 21, any of those you want to discuss quickly? 21. Now, in 21, one of the things we want to spend some time talking about today is simplifying and that kind of issue, although I don't want to overdo it. Okay, that's how I would write 21. Remember yesterday I told you to do 2 over x, I think? Didn't we say that? Did we talk about that? Oh, that was the other class. I like that. And this morning. That's right. I like it. No. I did forget to mention that with you guys. All right. Number 21 is an arcsecant. Arcsecant, right? Of x over 2. Now, secant and cosine have reciprocal values. They have reciprocal outputs is what they have. Secant and cosine have reciprocal outputs. So arc cosine and arcsecant have reciprocal inputs, because we interchange the inputs and outputs. I told you I'm not going to give you any arcsecant, arccosecant, or arcotangent. I won't. Okay, so I won't make you do this. But on 21, they give you arcsecant x over 2. There is a rule for arcsecant derivative, but I think the easiest thing is to do this. If you've got arcsecant of x over 2, change it to arccosine of 2 over x. They have reciprocal inputs. Okay? Now we can just do a regular derivative rule. Now I would write this inside as 2x to the negative 1 though, okay, because I know I'm going to have to do the derivative of the inside, so I'm getting ready for that. So the derivative would be negative 1 over square root 1 minus this squared, that's the u, times the u prime, which would be negative 2x to the negative 2. Okay? Now, if you go to look this one up in the back of the book, they do all kinds of weird kind of simplifying, which is fine. It's good simplifying, but it's just above and beyond what we need to do. I think we need to multiply this together and get those negatives to turn to positive, like so. And I think we ought to square that thing inside the square root. So this would be 4x to the negative 2. Power on a power you multiply. And that is good enough right there. Now, could you move that x down to the bottom? Yes, the 2 would not go with it. 2 would stay there. If you want to move that x down as an x squared, I'm fine with that. I don't think I would flip that around because then you start getting fractions you don't really need. Okay. I'm going to show you some complicated simplifying today, but there's not very much of that on the quiz. All right. If you're looking for simplifying, if you're looking up your answers in the back and you see how they did it, they do a lot more simplifying than you need to do. So don't get too hung up on that. Okay. But then if you're saying, well, how do I know if I was right then, right? If you can't get it to match, how do you know if you're right? Here's what I would do with my calculator. I would take your answer and type it into your calculator. Usually what will happen is a calculator will do some simplifying to it. Okay? Then look in the back of the book, or just use your calculator to do the derivative. Have your calculator do the derivative, and it'll usually do the same simplifying that it did when you put in your answer. Does that make sense? So have it do the derivative and see what it gets. Type in what you got for an answer, and it'll probably simplify it the same way, and then you can see if they match. So that's one way you can tell. If yours doesn't look the same as the back of the book, or doesn't look the same as what your calculator tells you it is, put your answer in and see if they match, and that's a pretty good way. Even then, sometimes they may not, and they might still be right, but that doesn't happen very often. All right. Another one. Yes?
When we simplify for you want us to like multiply numbers through and then...
I don't know about multiply numbers through, but if you've got two numbers that are multiplied together, you should multiply them together. If multiplying through, to me, seems like... if I ended up with a problem that, I mean, it's not going to be this simple, but if you ended up with something like that, I wouldn't distribute the 3 through there, but you could, right? And likewise, if you ended up with something that was 3x plus 6, maybe you did a product rule or something, and you ended up like this, do you have to take a 3 out? I wouldn't. I mean, you could, but there's no need to. Now, if you ended up with 3x plus 6 over 2, over 3, then yes, you should take a 3 out. Because if you take a 3 out, you could cancel, right? So in a product rule, a lot of times you can factor something out, but I don't think you need to. Okay, let's do a simple one here. E to the x sine x. Okay, let's say you had that. Okay, let's do a product rule. Y prime would be what? E to the x times sine left alone times the derivative of the second, cosine. Now, you could take an e to the x out of there, right? But there's really no need to. Okay, you can take an e to the x out and have sine plus cosine. I'm fine with that. Usually factoring is then if you can cancel something. Okay, and we'll get better at this as we do more of them and you see some examples. I want to look at one on page 195, and if there aren't any other questions there, I want to give you some more time. So if you got some more questions on page 190, you can ask me then. You can get the answer book out. A lot of you have already come in and checked some of those things out. But we can work on some things in. Let's take a look at number 8 on page 195. Anybody tried that one yet?
Yeah.
Okay.
Oh, yeah.
Some of you I know are doing some of the odd ones.
I was gonna say, is that one a really long?
It's an awful one. Yes, it would be a quite nasty.
I messed up
All
on
right.
it and then I had to redo it again. Yeah.
So let's talk about that one. Now keep in mind that this simplifying is a little bit above and beyond it. The process is not more than what I'd want you to be able to do. It's just that there's so many other messy things in there, it's easy to get lost. Okay? But, so let's take a look at this. So x to the 2/3 plus ln x, is that what it is? Over e to the x cosine 4x. All right, so this is going to be a quotient rule, right? First and foremost, it's a quotient rule. Now, I look down here and I can see a product rule in there too. But that's not going to come in until later. In the quotient rule, there'll come a time where I have to do the derivative of the bottom. At that time, I will have to do the product rule, okay? So we start with the derivative of the top. So that would be 2/3 x to the negative 1/3 plus 1 over x. Now, very important that I would put that in parentheses because of that plus sign in there. So the derivative of the top is that times the bottom left alone. Now, that doesn't need to be in parentheses because there aren't any plus signs in there. Okay? But you could put it in parentheses if you wanted to. That's what really throws people off. I think we get plus signs and time signs and what's all going on there with their algebra. Okay, then we got a minus. Then we got the top left alone because, again, with the plus sign, we're going to have to put that in parentheses. Times the derivative of the bottom. So now when I need a big set of parentheses, because I know that when I do the derivative of the bottom, I'm now going to be doing a product rule here, which has a plus in it. Now, let's talk about a couple of things here. First of all, something I've seen people do in a problem like this, especially a quotient rule. It's so messy up here, and you got to think so hard about everything that's going on here. When you get done, you forget what? The bottom square. So somebody in the other class said, you know what might be a good thing? As soon as you get a quotient rule like this, is put a big fraction bar and then just put the bottom square because that's easy to do. You don't have to do anything. You just copy it down and square it. Now that's all of that squared, okay, which would be both things squared, all right? But that's probably a good idea because I've seen people do that. I've seen people do the whole top and then forget to put the bottom, and then they miss it because of that. Kind of like the other day when I was saying when you have parentheses cubed, you should bring the 3 down, put your parentheses, put the square, because you're going to forget the square. You would hate to do a big problem like this, it's a big mess, and get it all right, and then forgot the 2 on an x cubed. So those are little things. All right, so let's do the product rule here. So derivative of the first is e to the x, cosine 4x left alone, plus e to the x left alone, and then the derivative of cosine. Okay, now let's think about this a minute. I could write it down. This is the one I always get. People get in danger of putting a minus, and then it looks like a minus, not a time. I'm going to do it. It's going to be negative sine 4x, and I'm going to have to kick out a 4. So before I write it, plus I'm running out of room, where can I put that negative? Could I bring it way over here or not? No, I tricked you. It's only this term that would be negative. I can put it right here. I can put it right here. Okay? All right? So I'm going to put that minus right there. Okay? And I'd like to put the 4 there as well. Okay? And then I'll have sine 4x. Sometimes the way you write it will help you in your next step, okay? But you wouldn't have to. You could have put e to the x times negative sine 4x times 4, right? You could have had that rearranged in here later. All right, now, many times, and we're going to do another example here in a minute where you'd be done, okay? Many times on as messy as they are, you're done. Now, at this point, I would hope we could get this part of it. By Tuesday, this part better be pretty easy, really. I mean, just to get to here. I mean, that's just, I mean, think about it. It's just a quotient rule. Each individual derivative is not tough as far as kicking out the 4. A product rule, you need to be good at a pretty basic product rule like this. Now, having it all thrown into one problem makes it kind of tough, tricky. I get that. But we need to have a lot more practice in by next Tuesday. So hopefully by next Tuesday, we can all get to here. Okay, now this one turns out to have something that can simplify. Okay, now what's going to normally simplify in a quotient rule is where you can factor something out of the top and cancel it with something that's in the bottom. Or you might have something that can combine, like there might have been a 2 in front of this, and so the 2 times the negative 4, well, or then this one, maybe you had a 2, and you can multiply it times that 4 or something like that. So those are the things you want to be on the lookout for. Now here's what I want to talk to you about. So in a quotient rule, you always have this part, the u prime v, minus this part. So what you're looking for is stuff you can factor out of each of those red groups. Now, does anybody see anything? Well, there is an e to the x, but then we'll get to that one. What about the cosine 4x? Can you factor out a cosine 4x? This red thing has cosine 4x as a factor, right? There's this quantity times that quantity times that quantity. So cosine 4x is a factor here. Is it a factor here? Because of that minus, it's not. Now, if we could take out a cosine in this parenthesis, then it would be a factor, but it's not. And that would have been good, because we could have canceled it with one that's down here. But let's talk about the e to the x. Is e to the x a factor in here?
Yes.
And then, once we factor it from there, we could factor it out of the red thing. Right? It's a little bit, let me see if I can simplify this. It'd be a little bit like having this. A times B times C. There's my e to the x right there, the B, okay? In my example. So A is like that first set of parentheses, then the B, then the C, okay? And then I got minus, and then I got that next set of parentheses, so I'll call that a D. And then in the next set of parentheses, I have a B E minus a B Q. All right. That's kind of what I have up on top there. Now this one, B is a factor. This one, I could take out. The D would just kind of hang out there, which the D is kind of like this piece. Okay? And in this set of parentheses here, I've got e to the x in each of these. So I could take out a b and then have that like so, right? So now, b is a factor of that, and b is a factor of that. And then I can pull out that b. Okay? So that's what's going on there. So up here I could take out an e to the x and have cosine 4x minus 4 sine 4x. Okay? And then times this stuff here. All right, so in this big red set of parentheses, I have this thing times that thing times that thing. So e to the x is a factor. So I can take out the e to the x there. And so what would I have? I'd have those parentheses times a cosine minus, then I'd have those parentheses times those parentheses, right? Those parentheses and those parentheses, I'd take out that e to the x. Okay, and down here, I would have what? Well, I'd have an e to the x. I'd have two of them actually, right? And I'd have two cosines, or a cosine squared. Right? Now I wrote two of them because I'm about to cancel one, right? So I'm going to cancel that, cancel that. So that seemed like a lot of work for very little return, really. And I would agree, that's not much return. And that is way deep in the weeds of simplifying compared to what you'll probably have to do. But the concept of what you had to do there is you might run into, where you can factor something out of each of these terms and cancel those something at the bottom. It's something you got to look for, okay? But this one's pretty extreme, all right? And I don't want you to get caught up in every single problem going, oh, God, what can I factor, or what can I simplify? Because most of the problems on there you will not have to simplify, okay? Let's do number 36 on that page. That's a similar one, and then it gives you an idea of what could possibly happen here. Okay, what does this one say? On top it's got a log, I think.
Yeah. Log is 10 of x.
Anybody tried this one? Over tangent of x. Okay. I hope you've spent some time on these on page 195. If you've done 10 a day, if you've gotten in about 10 or 20 of these, you're on your way to at least knowing what you don't know. I mean, that's the biggest part of practicing for these things, is knowing what you don't know, right? I mean, if you haven't done any of these, then you don't even have any idea where you're at as far as being ready for this gateway test, okay? So hopefully you've done a lot of those. Now, if you can get a lot done before Monday, that's good, but we're going to have a limited time that we can go over these, right? Monday will be our last day to talk about these. All right, so let's do a quotient rule on this. So the derivative of the top, tell me what to write. No? What's the outer function? 3 would come first, and then I might be smart to put the squared there. Log base 10 of x times Derivative of the inside, which is 1 over x. 1 over ln 10, that's the rule for log of another base. Times, don't forget the derivative of the bottom, that would be easy to do. And while I'm at it, I'm going to put my big old bar here so I don't forget to do the derivative of the bottom. The bottom squared, which would be tangent squared. Okay, I won't forget that. Okay, so this all was derivative of the top. Notice I don't need parentheses, I'm getting some funny looks. What questions? Anybody got questions here? Yeah, Cody? Where did we get the tangent from? It's u prime v, right? It's the derivative of the top. Yeah, so all this was derivative of the top times the bottom left alone. So yeah, u prime was pretty long here, right? And then there's the v. All right? Minus top left alone times the derivative of the bottom. Secant squared x. Good thing this was name on it. Okay? So here's our first big thing. So if I was to use the red again, and notice I didn't do any parentheses here because these were all times. There were nothing with a plus sign in it. So this was just a bunch of things multiplied, like a times b times c times d. I don't need parentheses around those if that's what I got. Okay? And then minus, and then I got this thing. So now, what can we do? Okay? Brenda's got an idea. Isn't there, there's a log base 10 of x, it's a factor here, 3 of them, and there's 2 of them here. So we can take out 2 of them. But can we cancel them? No. So go ahead and take them out if you want, but it wouldn't be necessary. It'd be kind of like that example I showed you a little bit ago, except it's 3x plus 6 over 7, right? I can take a 3 out of the top, which would be great, but I can't cancel it with the 7, so what's the point? So I would say don't do it, okay? So you could take out log base 10 of x squared, but I would just say don't even bother, okay? Nothing will cancel. And there's nothing really we can put together here. I mean, if this was a 1/2, you know, 3 times 1/2, we should put that together as a 3/2. But 3 times 1 over x, I wouldn't worry about. Now, if you want to make it 3 over x, put that together and put the ln 10 with it on the bottom, that's fine. But that's just kind of rearranging. It's not really combining or putting anything together, really. Okay? So to me, this would be one similar to the other one, but when you get to this point, you're pretty much done. Okay? And the reason was there was no logs down here on the bottom. Now, a good one, if you want to practice some more of this simplifying, take this same problem and flip it. Right? Take this same problem and flip it. Because now the logs will be on the bottom, and then when you do it up here, you'll have logs on the top too. And then I think you can do what Brenda said. I think in that one, you'd be able to pull out some logs and cancel it. So that'd be one you could maybe try if you want another one to practice. Okay? So that's pretty much done. And that's typical in the Gateway too, that there's going to be some like that, where you do that and you're finished. Okay? All right. What else? Anybody else got one from 195 that they tried that was kind of ugly or had questions about? 7? What was 7? Oh, I was thinking 7. E to the what? Cube root of u, so u to the 1/3, right? I mean, anytime you see a radical, you want to just immediately put it into a product, right? So this is a product rule. You know, this is an inside of that. That's the inside of that. So, but first and foremost, this is a product rule, right? So we got the first thing and the second thing. So the derivative of the first thing is e to the u squared times derivative of the inside, 2u, times the tangent left alone, plus e to the u squared left alone, times derivative of tangent. Derivative of tangent is secant squared, inside left alone, times derivative of the inside, which is 1/3 u to the negative 2/3. Right? Now, is there anything we can do with that? Once again, it looks to me like there's not. I mean, yeah, they both have an e to the u squared. Could I factor that out? Sure, but it doesn't cancel with anything. The product rule, it's not good because there's no by, right? And there's nothing really I can put together in this term, and there's nothing really I can put together in this term. So there you go. Now, one last comment on the canceling. If we get a canceling problem like this, if you have I'll just do a real basic one here. If I give you something like this with whole number powers, positive whole number powers, then yes, you should do some factoring. Take out an x squared, right? You get x to the 5th. Those would cancel. This would be x to the 3rd. You should do that. If you get something like this, which you will when you get into square roots, then don't worry about that one. It's possible here to factor out an x to the 1/2 or an x to the negative 1/2. Or you could split this up, right? I mean, we could have done that here too. We could just split this up. That's fine if you want to split it up. Okay, if you want to go that direction, you could. If you split this up, then you could just subtract powers. 1/2 take away 4, right? Be like x to the negative 7/2. And this one, negative 1/2 take away 4, that'd be 3x to the negative 9/2. Right? I mean, there's some stuff you could do there, but you wouldn't be required to. So if you get into one that's got square roots and stuff in a quotient rule and you got some fractional powers or some negative powers, you don't have to worry about factoring and canceling those. So don't have to worry about doing this, but you can if you want. But if they're whole number powers like this, then yeah, we should be doing that. Okay? So that's just kind of where I'm kind of drawing the line on the simplifying and what I want you to do. Again, if you look up answers in the back of the book that have these fraction powers, they're going to be simplified. So it'll be hard to match up your answers. All right, let's go ahead and give you the rest of this time to maybe get together some small groups, work on page 195. I'll pull up some things later on the website and just point out some of those things again. One thing to keep in mind on page 195, there's no implicit differentiation on that page with the x and y's mixed together, and there's no arcsine, arctangent, or arccosine on those either. But there are some on the website, and I'll show you some of that later. So if you want to get together and work through 195, answer books are up here. You can come check or pass them around, whatever. Come up and ask me for help when you need to.